Hi, dear friends. Let me have a more generalization of this uncertainty principle, which I believe is the only statement from science that says that we cannot. And in generalizing this principle, what we say is that this is the principle that prohibits our actions to actually understand the natural processes that are happening at the very microscopic level. And to be precise here is if we are not in a position to know the present situation, then in principle we can no way be in a position to know the future. So this is in fact this principle is negative, but it's so beautiful that uh, uh, it certainly comes up with the limits that we can have to understand nature at its basic level. Now, what would I start with is that talking about a particle, and if we have a particle and this particle uh, is moving, and this particle is equivalent to a wave group. It's equivalent to a wave group. Okay, that's discussed already. And there are fundamental limits of accuracy with which we can measure such particle. We can measure the properties of such particle like position, momentum, energy, so on and so forth. And and in order to make things clear, what is involved here is suppose if I take an example of a group of waves, and uh, what we see is that the particle that corresponds to this wave group may be located anywhere within the group at a given time. So the particle can be anywhere in this set of waves whose wave numbers are very very close to each other, whose frequencies are very very close to each other, and 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 certainly the probability density, that is what is that as as the square of the magnitude of square of this wave vector, this wave function, the, uh, is maximum in this case at the middle of the group of the waves that we have. And so it is most likely to be found at the middle of the group of waves that we have. And we may still find the particle anywhere other than that of the middle of that state. So it's not like that the probability of finding this particle at the other points is zero. No, there is some finite probability. And the narrower its wave group is, the more precisely a particle's position can be specified. That should be clear. And and at the same time, if we have a situation, say like this, okay, here lambda is seems to be immeasurable, but we are trying to bring down the position of the particle, and uh, and if we are able to measure the wavelength of the waves, I mean the wavelength of the waves in a narrower packet is not well defined, and there are not enough waves to measure this lambda accurately. So what does that mean? That means this means that since this lambda is h by mv, The particle's momentum is not a precise quantity. It's not a precise quantity. So, at the same time, if we take a series of momentum measurements, we will find a broad range of values for momentum. And on the other hand, if we have a situation like in which there is a more spread, if we have a wide wave group that we can see here, it clearly has a defined wavelength. We can see we have a clear defined wavelength, and the momentum that corresponds to this wavelength is therefore a precise quantity here, and a series of measurements will certainly give a narrow range of values. But at the same time, where is the particle located when I'm talking about this kind of configuration regarding the wave group of this particle? So here, what I see is the location of the particle is very uncertain, and there is certainty in terms of the momenta, because momenta is linked to the wavelength of this wave, and and uh, and the width of this group is now too great for us to be able to have say exactly where this particle is, and 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 thus what it means is that this is the basis that we have a statement that tells us that it is impossible to know both the exact position and the exact momentum of an object at the same time. The point is here, same time. And certainly, we all know that this principle was given by the great physicist Werner Heisenberg in 1927. And uh, and certainly, this statement is one of the most significant of physical laws that we can talk about in modern times. And and if we go in the quantum domain, and what we have is let us suppose that if we go with an argument that what we have in quantum mechanics now is we have only wave function, and wave function this wave function is used to specify the state of a particle. So using this wave function, we can specify the state of a particle. Okay. Now, what uncertainty principle does is the uncertainty principle sets a limit for the extent we can use this quantum mechanical state, what's called as psi, to specify the classical phase of a particle. And we what we try is we are trying to improve the situation regarding the location of the particle. The location of the particle. And 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 to have proper and precise specification of its momentum. That's what we try is we have set up the particle in the state psi. That is a superposition. That is a superposition of momenta states. Let us assume it's like that. So we have a state that we try to define in terms of momenta eigenstates. in which we have the momentum as h cross k. And having different k's in different eigenstates. You have different k's in different eigenstates. And to write down the wave function for such a system of momenta states where there is the superposition of the momenta, let us take the wave function, and this wave function is 1 by root 2 pi sigma ai e to the power of iota kx. Now, let me call this as equation 1 for the time being. This wave function with a vector, and this is equal to 1 by root 2 pi sigma ai e to the power of iota kx. And what is this ai? This ai is a representative of these momenta states that we have, where the values of k are slightly different. And what we do is we superpose the values of all these k's and to have the wave function psi. And now here we have an equation of discontinuity. Now what we try to do is that if the successive eigenvalues be so close together, okay, so close together, so that this k, what I was talking about, this k, what we generally call as propagation vector, which has a clear relation with wavelength, and that means it has a relation with momentum of the state. So what am I trying to tell here is that these k's, the difference between the k's is that much small that the summation that we have in the equation, this summation is replaced by the integration. So I'll be using 1 by under root of 2 minus infinity to infinity, then a of k and e to the power of iota k x, then dk. All right. So what does this ak represent here? If I take its psi star, if I take the square of its magnitude, the square of its magnitude is certainly giving me the probability of finding the momentum value. All right. Okay. Here we have momenta. Okay, and the square of magnitude of ak will give me the measure of momenta value, which I wrote down as h cross k. Okay. Now, if we choose this a of k that we have as some constant e to the power of minus sigma square times k minus k naught whole square by 2, where this sigma is the standard deviation. And this k naught is a reference k, and k is k. Now what is this? We have a Gaussian distribution in momentum space about the mean value k naught that's defined here when we define this a of k. So if I have to draw that distribution, so what I have is something like this. I have the Gaussian distribution, okay, and the center of this distribution is k naught. All right, and this distribution is such that the reciprocal of sigma is nearly equal to the small change in delta k. All right, and this distribution is basically the probability distribution of momentum that I was talking about. So this distribution is a of k whole square, and this is a representation of the amplitude of the Gaussian distribution. Now, talking about the width or the root mean square of the deviation of the distribution, which is 1 by sigma. So this delta px, if I have to write delta px, which is h cross k from its convention point of view, so I can write h cross delta k. And for this delta k, I can use 1 by sigma. So what am I going to have for delta px is h cross by sigma. Okay, and what would I like to do here is that that if I go back to this equation, if I go back to this equation, and I should have called this as 2, I should have called this as 3, and what am I trying to do is I would like to substitute this equation 3 in equation 2. Okay, so this should be my equation A. So substituting 3 in 2. So what would it look like? It's psi of x is integral minus infinity to infinity a by root 2 pi, yeah, and close it, e to the power of minus sigma square times k minus k naught whole square divided by 2 e to the power of iota kx dk. Okay, that should be the wave function. And the result of this equation that we will have would look like a by sigma e to the power of iota k naught x, then e to the power of minus x squared by 2 sigma squared. Now, to calculate the probability density, what should I do is to take the complex conjugate of this function and then multiply to psi of x. So in doing so, what am I going to get is I'm going to get psi star. Okay, so I have psi of x that's here, and I would like to multiply it to its complex conjugate, and certainly this e to the power of iota k naught x will die, and what will remain there is a by sigma whole square e to the power of minus x square by sigma square. Okay, that should be the case. Now, if we think in a very articulative sense, in arbitrarily, what we have to do is we have to normalize this probability density, and when we'll be able to normalize this probability density, from there we can have the value of this a. So, what should I use here is normalization. Okay, so what will be normalization? Minus infinity to infinity. Then we will have psi of x whole square. Then we will have dx equals 1. So it will be minus infinity to infinity. This a by sigma square will be out, okay? This will be out. What will remain inside is e to the power of minus x square by sigma square dx is equal to 1. All right, and the value of this standard integral minus infinity to infinity e to the power of minus x squared by sigma squared dx is 1. If that's the case, then what we have is a squared by sigma squared is equal to 1. Okay, uh, uh, okay, its value is it if it was alpha. Okay, what we have e to the power of minus x squared by alpha squared dx. Uh, it is alpha under root pi. Okay, so the value of this integral is sigma under root of pi. So a mistake here. So the value of this standard integral is a under root of pi. So what we have in this equation is, let me have a new page. Okay, so what we have is a squared by sigma squared times alpha under root of pi is equal to 1. This is what we have. So we can, no, it's not alpha, it's sigma. Okay, so it's sigma. This sigma and square will cancel. This sigma refers here to the standard deviation, and this a square will be, the sigma will go up, divided by under root of pi. Okay, that should be the case. Then what should be a? It should be, yeah, what I have here is a square and sigma square. This sigma and this sigma, they are going to cancel. Then what I will have is sigma will go up and root pi. I'm not sure about the value of this standard integral. I hope you'll find it, but I can think of the result here, and the result is that this a square is sigma by root pi, and I think that's correct. And this is, so if we have to write for a, then a will be under root of sigma by pi. Yeah, that should be the case. Now the point is that we have had the factor one by under root of pi that we had used in some equation. Okay. Okay, yeah, here what we have in the original wave function, we have psi equal to 1 by root 2 pi, and we have normalized this equation. Here we have it, and here we have psi equal to 1 by root 2 pi, and we have normalized it, and we have calculated the normalization factor on the momentum eigenfunction in this infinite domain that we have. Hence, what we have is hence the superposition state of psi of x that we have defined. It certainly gives us a Gaussian distribution. It gives us Gaussian distribution in both the momentum space and in the position space. We have the same Gaussian distribution for the position, and I would like to draw that. I mean, we have a distribution, and the distribution is Gaussian, and the amplitude of this position state is a square by sigma square that we have defined already, and the probability of position that we have here is say phi of x whole square, and and this is my sigma, which is equal to delta x. So the beauty of this transformation is that we have Gaussian distributions for both position state and the momentum state. So in addition to this, the mean deviation in the two measurements that we have, the measurement in terms of momentum and position, they are interrelated, they are interconnected, and they are interconnected by the equations that we have drafted out. And and the width of the Gaussian distribution in the position of this Gaussian distribution is sigma. So this delta x here, what is this delta x is sigma, and we have already had delta p, and we have already evaluated delta px, and that delta px is h cross. That delta px is basically h cross by sigma. Okay, this is the case. And now if we multiply the two standard deviations to uncertainties, the uncertainty of position and the uncertainty of momentum, the output is, this is delta x, this is delta px, is sigma times h cross by sigma. So from here we have the wonderful equation, the wonderful inequality, the wonderful argument that says that you have the uncertainty in the measurement of position if you have certainty in the measure of momentum, and this is greater or equal to h cross. So these two sigmas are going to cancel, and when we decrease the uncertainty of the particle that we have here in terms of position, we are certainly increasing the uncertainty of the particle's momentum, and a precise knowledge of one can be obtained only at the expense of the precision of the other. So with this, I would like to end this presentation, and I hope my students, my friends, whosoever is watching these videos, they will like the video, they will share it, and so that it becomes, so that I feel great about it, so that I feel good about it, and what should I say? I should say goodbye and good luck to everybody there. Have a nice time, and enjoy your lives. Be good humans. Love each other, and there's nothing in our hands. Whatever it is, we should use that thing to live a positive life, a life of brotherhood, a life of love. And this message is universal. It's not for the people of my country alone. It's for the people of the whole world. No doubt, at the first it's for my country, then certainly it goes to the rest of the world. So with this, I would like to say bye and good luck.